So now we have a scale that tells us when a solution is acidic, and it'll tell us how acidic a solution is, right? The lower the pH value is, the more acidic a solution is. The higher the pH value is, the more basic a solution is. So that's useful, and that will be information that we're going to want to know. How acidic is this solution, right? And all those other kinds of things, because it allows us to compare. If this compound is acidic, how acidic is it? Is it more acidic than this other compound? Is it less acidic, et cetera, right? And these are all physical properties that we're going to want to know when we set up reactions and need to have, okay, I need to make this thing acidic enough that an H plus gets transferred to this other thing. You need to know, is this compound, like, is it strong enough to do that, right? So acid strength is an important thing. So let's talk about acid strength. Today we're going to mostly talk about strong acids and strong bases, and then we'll briefly touch on weak acids as we get towards the end of this thing. Okay. So what is a strong acid? A strong acid is when the equilibrium of the acid-base reaction lies very far toward the conjugate base. Right? And remember that the conjugate base is on the product side. Right? So you're looking for things like a large KEQ. Right? So you have your acid plus water makes hydronium plus conjugate base. Right? If the equilibrium favors the product side, then you have a strong acid, right? So large KEQs tend to favor the products, as we know from previous work. Strong acids have KEQs that favor the products. Furthermore, because all of these reactions kind of work in reverse as well, right? What this means is that if we have a strong acid on this side, if this acid is a strong acid, that means that this base is a weak base, right? So these two things are always paired together, right? A strong acid will always have a weak conjugate base, and vice versa. If you have a strong base, that means that you have a weak conjugate acid. These reactions are always paired this way because, of course, the reactions go in both directions. So if we use a strong acid, like let's say that we use HCl, right? Hydrochloric acid is a strong acid. I don't think I'll get any argument on that point. When these two things react, of course, we get H3O plus and we get Cl minus. And so Cl minus ends up being our conjugate base. And so we compare which of these things is the stronger acid, which of these things is a stronger base. HCl is the strongest acid around, and Cl minus is the weakest base, right? Because they are conjugates of each other, they always kind of pair that way. Okay? So what are some strong acids? Let's list some strong acids. Strong acids: HCl, HBr, HI. HI is an incredibly strong acid. Some would argue that it's not really an acid even. It's just the equilibrium lies so far to this right side that mostly if you have a mixture of HI, you really don't have any HI around. It's all just hydronium ion. So it's very, very strong. Nitric acid, HNO3, another good strong acid. Sulfuric acid, H2SO4, and perchloric acid, HClO4. Right? So these are the 6 most common strong acids that you're going to run across. And there's nothing to say about these except here's a list of strong acids. Try and remember these and recognize them. Right? And so a question you might get asked is, well, okay, what's the pH of an 0.3 molar solution of HNO3? So we could write out the equation, right? And HNO3 plus H2O yields hydronium ion plus the conjugate base of HNO3, which would just be NO3 minus, right? We lose the H and that becomes negative. But that equation isn't really necessary because we know that this is a strong acid. So because HNO3 is a strong acid, we can say that the concentration of H plus is more or less 0.3 molar. Right? Now, is it exactly 0.3 molar? There might be a little bit of wiggle room there, but for the most part, right, this is the equilibrium of this reaction lies very far to the right, to the product side, right? Because it's a strong acid, that's how we define strong acids. They have large KEQs. That means that the majority of the concentration, right, the majority of the components of this reaction are going to be the products. And so the concentration of H plus is pretty much 0.3 molar. So if we wanted to find the pH of this, all we have to do, pH equals the negative log of the concentration of H plus, which is 0.3 molar. And so this comes out to be 0.5. So the pH of this 0.3 molar solution of HNO3 is very, very, very low, right? It's 0.5. And so that means that this is a very, very, very acidic solution, which of course, if you're making a solution of nitric acid, you would hope that you're getting a solution, an acidic solution. And in fact, you do. All right, so let's look at strong bases. Strong bases mostly all have kind of the same format, right? Strong bases are mostly just hydroxide ions. So you have sodium hydroxide, potassium hydroxide. You can have magnesium hydroxide, although you have two hydroxide ions in that case, right? But those kinds of things, it's always going to be OH minus. So if you have OH minus as a salt, that is a strong base, which of course makes sense because what you're going to do, if you write out that reaction, you have NaOH plus H2O is going to make NaOH and H2O, where H2O is the conjugate acid, right? So this is kind of a weird one because sodium hydroxide basically just produces itself in reaction. But of course, what that means is that if you know the concentration of sodium hydroxide, you know the concentration of hydroxide that's in your solution. And so let's find the pH of an 0.3 molar solution of NaOH. So we can find that. What is the concentration of H plus? We don't know that right off the bat. We know the concentration of OH minus. Concentration of OH minus is 0.3 molar, right? So how would we figure out the concentration of H plus from that? We could use Kw, right? Because we know that concentration of H plus times concentration of OH minus equals 1 times 10 to the negative 14th. So we could say that the concentration of H plus equals 1 times 10 to the negative 14th divided by 0.3 molar, right? And that's using Kw to figure that out. And then we would have to take the negative log of this value. Now, we can do that because we can use the properties of logs to kind of make this work out better. And what we'll end up with is we have the negative log of 10 to the negative 14th minus the negative log of 0.3, right? And this is because when you have a quotient, when you have a ratio here, the log of the quotient is the difference of the logs. So we can take the log of minus 14, or log of 10 to the minus 14th, and subtract the log of the denominator. Right? So this is obviously 14. I'm running out of space, but I don't have another slide, so I'm going to squish this in. And then we have the log of the negative log of 0.3, which is 0.5. We know that from above. And so the pH of a 0.3 molar solution of OH minus is 13.5. So it is incredibly basic, as we would expect, right? So again, if you add a strong base to something, you're going to get a basic solution. Okay, so now, right, the other thing we can do is if we know, right, if we know that the negative log of 0.3 is 0.5, we can just take 14 minus that 0.5 and get the pH of that solution because we know that, right, OH minus and H plus are related that way. We could figure out the POH basically and then take 14 minus that because remember, whoops, the POH plus the pH is going to be equal to 14. So if we had just taken the negative log of 0.3 to find the pOH, that would give us 0.5. We take 14 minus that, that gives us our pH. Okay? So there's a couple of ways around that. But either way, no matter how you do it, you're going to get to 13.5. And you're usually going to get there by taking 14 minus 0.5. So strong acids, strong bases. Again, the strong acid list, there's 6 acids on there. You should just memorize those, write them down somewhere that you can find it, because HBr, HCl, HI, nitric acid, sulfuric acid, and perchloric acid, those are the ones that we're going to use as our stand-ins for strong bases. There are other strong acids. Oh my gosh, strong acids. There are other strong acids out there, but they're not the ones that we're really going to use too much in this course, right? So remember those, and anytime you need to figure out the pH of a solution of a strong acid, it's very easy, because we assume that all of the acid has become hydronium ion, and then we can just take the negative log of that concentration and figure it out from there. Okay, so that's the pH system. We've done the pH system. We've talked about strong acids. We've talked about strong bases. The only thing left is weak acids, and they are complicated. So we are going to spend some extra time on those. So that'll be the next thing. We'll get to weak acids, because in weak acids, of course, now KEQ is going to be very small, and so we don't get a complete dissociation into H plus or hydronium ion. And so now we have to figure out if it's not going all the way to our full concentration of H plus, how far does it go? What is the pH, etc., etc. So all of those calculations and more in the next couple videos.